Now I'm going to start to talk about the method of sections. Remember when we started to analyze the truss, I was saying that one method to analyze the truss was the method of join. So basically what we did was that we went ahead, we find all the reaction on the supports first, and then we go and inspect the joints one by one. We choose the joints that has only two unknown or one unknown. And then we write the equilibrium equation for every joint. We find the unknown in that joint, and then we move to the next joint, and then to the next joint, and to the next joint, until we find the forces in all the joints in our truss. The problem with that is that first of that method is a relatively easy, straightforward method, but the problem with that is tedious, and one shortcoming for that method is if we look for the force in a specific member, that's very hard to do that without calculating the force in all the members. In other words, the joints method is good when we want to analyze the entire truss. But what if we only want to find the force in 2, 3, 4 members, in very limited number of members? In those cases, then using the method of joints, we are ended up finding the force in so many members that we don't need them, because we have to start going joint by joint until we reach to the joint that are those particular members that we look for are connected to those joints. Because of that, there's another method that we will use to analyze the truss, and this method is good only we need to find the limited number of forces in the truss. Otherwise, so if we need to find all the forces in the truss, all the forces in the entire truss, all the internal forces, we will use the method of joints. If we need to only find 2, 3 limited number of forces in the truss, we will use the method of section, and for our purpose. So how that method of section is work. So let's consider a truss, and we'll explain how it works. So assume I have a truss like that. And so I have a truss like that. So we call it A, B, C, D, E, F. And there's a force applying here. Now assume I only need to find forces in member BC, member FC, and member EC. So these are the three, so I'm gonna just put the markers. So these three. So I want to find the force in BC, I want to find in FC, I want to find the force in EC. So these are the ones I put the mark beside. So only I need these three. I don't need forces in the rest of the truss. I only need forces in these three let's say members. So what we are going to do is that, again, remember, if it's a 2D, the very first thing we are going to do is that if all external forces are not in the x and y direction, first of all find them all find their component in the x and y direction. That's the very first step we need to do. The second step is that in most cases we need the let's say the reaction of the support. So go ahead and find the reaction of the support for the second step. So find the reaction of the support, and then that's how we are going to do that. So assume I find the reaction of the support. I have the reaction of support here is the AY and it's the AX, and here is the DY. So these are the reaction of support I have. at point A, at joint A, at joint D, and this is the external force I have. The next step is that we are gonna cut through the truss, through the member we want to force in those members. So remember, we are cutting through the truss, through the members that we need the force in those members. And remember, it should not be more than 3. We cannot cut more than 3 at the same time. So we never cut more than 3 members at the same time. But here, so we are gonna say that I need the force in EF, in EC, and in BC. So EF, EC, BC, these 3, I'm gonna cut the truss through those 3 members. So I cut the truss through those 3 members, and then I split the truss to 2. So I'm gonna split the truss into 2, and then I will draw each of those 2 sections separately. So I'm gonna draw them. I might try to draw them here, but so I will try to put them here. So I will draw each of them separately. So I would first draw the this side, the left hand side. So it's going to be this part, and then I cut it through. So I only have it until here, because I cut it here, I split it to 2 at that part. So it's gonna, I have this section, I have this, and I have this. So this one is point A. So it's a point A. This is A, this is B, and this is F. Then I would draw the other half as well. So I would draw the right hand side as well. So let's start at this point. So I will have it so this is sort, and also I have until here, so I have it like that. So this is the half of it, this is the half of it, and this is the half of it. So these are the force I have, and so it's going to be AB, and it's going to be point C, it's going to be point D, and it's going to be point E. So I split it to 2. Then I will put all the external forces I have on them. So I have AX here, I have AY here at joint A. Also I have DY here at joint D. Also I have the force, the external force, assume I call it P, I have external force P also at point B. So I would put all the external forces exactly where they are. After that, I will draw the internal forces. And remember, as we did in the joint method, always we draw the internal forces as a tension. Always as a tension. It means that they move away from the object or joint or whatever we are drawing from. So they're always move away. So here I have the internal forces of F, FE. So whatever I have here, I'm going to have the reaction of that equal and opposite on the other side. So also I have F. The same here, I'm going to have F, FC. The same, I will have the same here on the other side. So it's going to be F, FC. And here, I'm going to have F, B, C. And here, I have F, B, C. So I draw the external forces on both halves. So it's the one half and the other half. So this is how I cut them through. Okay. So I cut them through, split it to 2, put all the external forces, and then put all the internal forces as a tension on them. After that, I will choose one of these two to start analyzing and find the forces I want to for my calculation. For example, here I'm gonna choose the right hand side, and the reason is that because there's only one external forces. Here I have three external forces. Here only I have one external force, so I have less forces. I would choose the right hand side. I can choose the left hand side too, so it doesn't matter. You will choose one of the two sides, any of them that is easier to do. So assume I'm gonna choose the right hand side, and then if I write for the right hand side, if I write the sigma f x is 0, sorry, if I write the sigma f y is 0 for the right hand side, if I write the sigma f y is 0, then from there I can calculate the whatever value is that. So I can calculate the value for ffc, because this is the only one has the y component in the unknown, these three unknown. This is the only one that has the y component. So if I write the sigma fy, I can easily find the value for that. Then if I write the sigma fx is 0, both of these two unknown would be in my equation. I cannot get anything out of that. So I have to write the moment. Probably the best point to write the moment about that is that point C. So I can write the moment about point C 0. If I write the moment about joint C 0, FBC passed through it, so it doesn't have moment. FFC passed through it, so it doesn't have moment. So only two forces that has moment about point 0 is FFE and dy. So I can find the FFE from here. And eventually, if I write sigma f x is 0, then I can find the value for FBC, because that's the only unknown left. I can do it also for the other side as well. Remember, don't get confused. Here I use the moment equation. We can use the moment equation for entire truss, or as here as part of the truss. We cannot use the moment equation for the joint. There is no moment at the joint because they are pinned. So we don't use the moment equation at single joint. When we do the method of joint, remember, we never use the moment equation. There is no moment at the joint if we separate the force at the joint. But if we choose the entire truss or part of the truss, we can use the moment equation for that entire truss or that one. In other words, I will consider this entire truss as a rigid body, or I will consider the right hand side of this truss as a rigid body, or I consider the left hand side of this truss as a rigid body and write the equilibrium equation for them. And from those equilibrium equation, those three equations, I will get and calculate the unknown I need for that. Now let's look at the example to see how we do the method of section. Assume I have a truss look like that. Also I have a member here. So assume I have a truss look like that, and I want to find the forces in CE, BE, and BD. So these three members, I want to find forces in those three members. So again, remember, if we need to find forces in entire truss, we use the method of joints. But if we need to find forces in limited number of members, we will use the method of section, and this is what we are going to do. So before I start doing that, first, if external forces are not in the x or y direction, find them in the x or y direction, find their component in the x and y direction. Second, since in most cases we need the reaction of the support, just go ahead and find the reaction of support for that truss. So if I want to look at that, I'm going to draw it on the other side. So first of all, I consider as entire truss as a rigid body, and then I will analyze that. So if I have my truss look like that, and then I have 100 Newton here, and I have two reaction forces at A, so I have a AY and AX, and I have a one reaction at GY. So if I have this, if I go ahead and write the sigma fx is 0, so sigma fx is 0, it gives me AX is 0, because we don't have any forces in the x direction, so AX is going to be 0. Then if I write sigma fy is 0, I'm not going to get anything because I have two unknowns, so I'm going to write sigma m about point A is 0. If I write the sigma m about point A is 0, then, and assume the counterclockwise is positive, then here I have, because 100 respect to point A, about point A is going to rotate the whole truss, the entire truss as a clockwise, so it's going to be negative times 100, and the normal distance between 100 and joint A is this distance, which is going to be 0, so times 3. The GY is going to rotate the entire truss about 0.8, rotated as a counterclockwise, so it's going to be positive, so it's going to be positive GY, and the normal distance between GY and A is from here to here, which is going to be 9, so it's going to times 9, it's going to be 0. Therefore I would calculate the GY as 33.33 Newton. Then if I write the sigma fy is 0, I have AY plus GY minus 100 is 0. I have AY, GY, and 1 is 100. Therefore, the AY plus 33.33 minus 100 is 0. Therefore, AY would become 66.67 Newton. So I will calculate all the reaction here. I'm going to put the reaction, write down the reaction there so I can use it later. So I know the AX is 0, so I don't need it. So I have the AY is 66.67. So it's going to be, I have AY 66.67 here. And also I have GY is 33.33 Newton here. So now I have my external forces, and all the forces are in the X and Y direction. Now I'm going to cut through the truss. Remember, cut through the truss through the members I want to find the force in those members. So I want to find the force through BD, BE, and CE, these three. So I'm going to cut through the truss through those three and split it into two. So I will cut through it and split the truss into two sections. So if I cut through it, and I'm going to draw it and split it in two sections, I will have the left hand side, which would be something like that. So it's going to be point A, C, and point B. And then I have the right hand side, which would be something like that. So I cut it through, split it into, I cut through, split it into two, and then I have the G here, node E here, node D here, and now I'm gonna draw the external forces there. So I have 66.66 here, I have 100 here, and just I would replace the support with the reactions. Just easy, so remove that, and I have 33.33 here. So I have all the external forces. Then I would put all the internal forces as a tension there. So I have a FBD, and then I have the reaction of that equal and opposite of that, FBD. Same here, I have FBE, and I have the reaction of that FBE, and then I have here FCE, and I have the reaction of that FCE right on the other side. So basically I cut through it and I split it into two parts. Now I will choose one of the parts that I think is easier to do the analysis. I will choose here the left hand side. You can also choose the right hand side, doesn't matter either of them. Here it doesn't matter. Probably the right hand side is a little bit easier because it has only one external forces. Here we have two external forces on the right hand side, but I will choose the right hand side. You can choose the left hand side. So look at that, either of them that you think is easier to work with, choose that one and start work. So I would draw the this side again up here. So this is what I'm gonna have. So this is what I have. This is a joint A, this is a joint B, this is a joint C, and then I have .66 here, I have 100 here, and I have FBD here, FBE here, and FCE at this point. I want to start analyzing. Before I start on, probably it's good to find that angle here. So look at this angle here. I would use so this angle here, so it's a theta. This theta here, I know that in this triangle, this is 4, this is 3. So I have a triangle here. This is 4, this is 3, this is gonna be 5. If you calculate that, this is a triangle of 3, 4, and then this one is gonna be 5. So the same here, if I continue these two, let me draw. So it's gonna FC down here, FC. So if I draw that, it's going to give me that theta here, that theta. And if I look at in this triangle here, the triangle I have here, the triangle looks like this. So I'm going to draw the triangle again here. So that triangle is 3, 4, 5, and this is a theta. Therefore, cosine theta is 3/5, and sine theta is 4/5. So if I draw that triangle, this triangle again here, so this is this internal triangle, I draw it again here, and this is a theta. So this is a 4, this is 3, therefore this one would be 5. We can calculate it as a square root of 4 squared from 3 squared, the square root of that. So it's going to be 5. So that length is going to be 5. If it is 3, this 4, this is going to be 5. And then the cosine theta is 3/5, and the sine theta is 5/5. It is 4/5. Now I have this, everything I need here on this section. So I draw this section, the left section. Now I'm going to write the equilibrium equation for that to find what I need. So the first thing I probably would write it is I would write the sigma Fy is 0, because here both of FBD and FC are in the x direction. They don't have any y component The only one that has a y component is FBE. Therefore, if I write that, it's going to be 66.66 minus 100 and minus FBE and sine theta. So the sine theta is going to be 0. So we know the sine theta already is 4 over 5. Sine theta is 4 over 5. So therefore, I can get the FBE from this equation to become equal to negative 41.66. So this is the value I have for the FB if I write that equation. Then after I have the FBE, I can go ahead and write the equation sigma m about any point. So probably is this one, because if I write the sigma fx is 0, these two, both of them are unknown in the x direction. It's not going to give me anything. So I would write sigma m about point B0. And the reason is that FBE go through point B, so it doesn't have any moment. FBD go through point B, so it doesn't have any moment either. So only FCE is going to have the moment. So if I write the sigma m about B is 0, then if I look at it here, B is about, let's have the counterclockwise positive. Then 66 is going to rotate it clockwise, so it's going to be negative about point E. So 66 about point B is going to rotate it. So it's going to be negative 66, 66. And the normal distance between 66 is 3 times 3. The 100 goes through point B, doesn't have any moment because it goes through point B, so there's no moment. The FBD goes through point B, doesn't have any moment. The FBE goes through point, doesn't have any moment. This one has a moment and the FCE has a moment. It rotated about point B counterclockwise, so it's going to be positive, and it's going to be FCE. And the normal distance between the FCE and B, the normal distance is here, which is going to be 4 times 4 would be 0. Therefore, FCE can calculate it as 50 Newton. And then at the end we can simply write the sigma Fy, sigma Fx is 0. Then I would have the FBD plus FCE plus FBE cosine theta is 0. Therefore, I know the FBE, FBD is the one we look for. FCE is 50 Newton. So it's going to be FBD plus FCE, which is 50 Newton, plus FBE is negative 41.66, and cosine theta is 3.0/5 is 0. Therefore, FBD would be calculated as negative 25 Newton. We could have done the same thing also for the right hand side. We could have chose the right hand side, draw the right hand side, and then you have the forces and do the equilibrium equation for the right hand side. You will get the same result, and this is how we do that. So one more time, if we need to calculate the forces in all members, we will use the joint method. If we need to calculate the forces in limited number of members, we use the sections method. And the way we are doing that, first find all the forces in the x1 y direction. If they are not already in the x y direction, find their component in the x1 y direction. then find the support reaction. After that, cut the truss through the members that you want to find the forces. And remember, they should not be more than 3 because we have only 3 equations. So we cannot cut more than 3 elements. So make sure you're splitting the truss by cutting through the elements where you need the force in those elements. Then put all the external forces first. Then put all the internal forces on both sides as a tension. And after that, choose the one of the side that you think is easier to solve and write the equilibrium equation for that side and find all the unknowns in that side of the truss. Remember, when we split it into, when we consider either of the sides, for example, when we consider here the left hand side, we consider the whole left hand side as a solid, as a rigid body. So we consider this as one object, as a rigid body, and we do the equation of equilibrium for the rigid body for that left hand side of the truss. If we choose the right hand side, we would do the same thing, because for example here that left hand side should not go inverted, it should be a stay at equilibrium. So we can consider it as a rigid body. We write the equilibrium for the rigid body, we write the equilibrium equations for the rigid body, and we find all the unknowns in that part of the truss.